Skin depth and power flow. So the only two topics we have here are skin depth and power flow. These are a bit more advanced topics about waves, so let's get right into it. Skin depth. So when we're talking about skin depth, normally we're talking about conductors. And in conductors, the loss is extremely high. And so if a wave manages to penetrate into the metal, it decays very quickly. So what we're looking at here with the green line is a wave, and it's oscillating, it's pushing power along, but this envelope, this red line, is showing the decay of that wave, and it's decaying e to the minus alpha z. So in a metal, that decays very quickly, and we need some kind of number that just characterizes about how far a wave penetrates into a metal before it decays to zero. And so what we do is we define this 1 over e point. The distance that it takes for it to decay to the 1 over e point is the skin depth. And since it's decaying as e to the minus alpha z, the skin depth then is just 1 divided by alpha. Well, we know alpha in terms of our fundamental parameters, so we can put our skin depth in terms of those fundamental parameters. And in fact, we can then even relate the skin depth to our impedance. But the whole point about skin depth is it's about how far a wave penetrates into the metal, and metals, the skin depth is usually very, very small. And there's some interesting consequences of this. At DC, we're not talking about waves, and this is something we discussed in electrostatics. And so the current tends to distribute itself evenly throughout a conductor. So here we're looking at a conductor of some conductivity sigma, and then the green arrows here is a way that I'm trying to visualize the current density, and it is uniform throughout the conductor. So if we look at the conductor area, it's pi r squared, where r is the radius of the conductor. So if we were to calculate the DC resistance of this chunk of conductor, well, it's the length of the conductor divided by the area and also divided by the conductivity. So then we can throw an L over sigma r squared, and that is the DC resistance of this chunk of metal. Now what we'll do is talk about the AC resistance. We will let this be a high frequency, and what we'll see is that we're not utilizing all of the conductor now due to the skin depth. Therefore, the resistance goes up, and things get worse at high frequencies. I say worse, assuming that higher resistance will be worse for your signal. So now at high frequencies, the wave penetrates into the metal but decays very quickly. And if we were to try to visualize the current and how it's utilizing the conductor, this is the way it's visualizing. Notice the current is strongest on the outside of the conductor, and it decays moving away from the surface. And then, of course, we're characterizing this penetration depth with the skin depth. So really, the current is not utilizing the entire conductor. This inner part of the conductor is not being utilized at all. So if we have this skin depth here, we can define the area that it is actually utilizing as just 2 pi r delta. That's a way to approximate the area for a high frequency signal. So now the resistance to AC is the length divided by the AC area and also divided by sigma. And so we can then plug in our formula for the area, and we get this for AC resistance. And that is different than the DC resistance because we're not utilizing the entire conductor. So we're going to summarize what we've just said and then talk about some advantages and drawbacks of skin depth. It actually does have some advantages. So high frequencies experience a lot of loss in a conductor, so they only penetrate so far. The distance that they penetrate is called the skin depth, and we saw that. And so because of the skin depth at high frequencies aren't utilizing all of the conductor. And so that makes the overall resistance go up because the effective area that the current is distributing out over is less. Now the drawbacks of this is that high frequencies experience more loss. They're not utilizing all of the conductor. This also means that how much loss it is becomes frequency dependent, and so this also distorts our signals. That's bad. Now you might be surprised that skin depth actually does have some advantages. One thing is, if our signal is not utilizing the inside of the conductor, we can make our conductors hollow with no cost electromagnetically, so they can be cheaper and lighter. Or we could make our conductors with something else going in the middle. Maybe we want really high conductivity, so maybe we'll put copper on the outside of the something, and then we'll use a cheap metal on the inside, something like aluminum. So we can use this skin depth to our advantage as well. Our next topic, power flow. I'm skipping a long derivation here, but we can start with Maxwell's equations, and it would take us probably 10 minutes, 20 minutes maybe to go through the derivation, and we would end up at this big equation that we're showing at the bottom that is called Poynting's theorem. And this really describes what happens to the energy in a system. So we're showing a system here in gray, an enclosed system, and we can add energy to it by propagating waves into this area, and we can take energy out, and so there's power leaving that volume. Now inside this closed system, we have a loss mechanism. There's ohmic loss that usually converts the electromagnetic energy to heat. But we can also be storing magnetic energy and storing electric energy, either in inductors and capacitors or the permeability and the permittivity of materials. There's various ways to store that energy. So other than this, there's nothing else that can happen to energy without there being like a nuclear reaction, and we're definitely not talking about that. So all of that comes from this equation, and it's not derived with knowledge of Poynting vectors or energy density or all that. In fact, this equation is derived first, and we get all that from this equation. So when we arrange it, on the left, we see E cross H, and it turns out this is talking about power leaving the volume. And in fact, if power is entering, then we would get a negative number here. We have this other term where we recognize these expressions when we talked about energy density. So there's a negative sign here. So we describe this as the rate of decrease of stored electric and magnetic energy that's either stored in inductors and capacitors or a permeable or permittivity kind of medium. And then this last term, which we also recognize from our discussion in electrostatics, is the ohmic power being dissipated, because we have this conductivity term sitting here. So without a nuclear reaction happening, this is the only thing that can happen to our energy. And maybe we're asking, well, what if there's a light bulb here or we're turning an electric motor? Well, we still would lump that in with the ohmic loss, even though technically we're just converting electrical to some other form, but to this framework, it appears like an ohmic loss. So from Poynting's theorem, we look at this one term that we know is responsible for power coming into and out of our closed system. But what we see is this interesting cross product of E and H that we haven't seen before. Well, we're doing an integration here, and anytime we integrate something, a lot of times that thing that we're integrating we can interpret as a density. And since we're integrating to get total power, the argument on the inside must be a power density. And so in fact, that's how we define this cross product, as a power density with units of watts per meter squared. And so we give this a special name, and it's called the Poynting vector. This isn't pointing as in pointing your finger. This is a person's last name, Poynting. And in a way that's kind of convenient, or maybe even confusing, because the Poynting vector also points in the direction the wave is going. The Poynting vector and our wave vector are parallel. They're in the same direction. So when we talked about waves, we had this point where E and H in the direction of the wave are all perpendicular to each other. Well, E and H are still perpendicular to the Poynting vector. And we see this a separate way now, because we calculate the Poynting vector as the cross product of E and H. So the Poynting vector, just from this, absolutely must be perpendicular to E and H. All right, so our Poynting vector, E cross H, is power density, watts per meter squared, and we would have to integrate it to add it all up to get a total power. Let's look at the instantaneous Poynting vector. So by instantaneous, we're looking at an instant in time. So we need to write our wave equation, or not wave equations, but our solutions to that, our plane waves, in time domain form. So we have an electric field and a magnetic field, and we have loss built in here, so it's decaying as e to the minus alpha z. And then there's this cosine term that has our frequency oscillations and then also our spatial oscillations here. So our wave's traveling in the positive z direction, and the electric field is polarized in the x direction. Well, if the wave is traveling in z, the electric field's in the x direction, our magnetic field is in the y direction. The magnitude of the magnetic field is the magnitude of the electric field divided by the magnitude of impedance. It decays the same way. It oscillates in time the same way. It oscillates in space the same way as the electric field, but there is this phase, potential phase, due to the impedance, if there's any loss in the material. All right, so we have our general expressions for E and H. We have our expression for the Poynting vector, E cross H. So we have some math to do. So we can plug in these two expressions for E and H, and we can start calculating the cross product. And when we do that, we end up here. And this is our final expression for the instantaneous Poynting vector. And we see that there's two terms here. The first term has a cosine with the angle of impedance. So this is a constant. This is decay. This is constant. There's nothing oscillating or fluctuating here. And so this term describes our sort of constant overall flow of power. Now this other term has a cosine with a 2 omega t, a 2 beta z, so this is oscillating rather rapidly. So in terms of the instantaneous Poynting vector, there's this rapidly oscillating, fluctuating power flow. That's kind of weird, huh? Let's visualize this. So we're looking at a wave propagating in the z direction. I've labeled the wavelength here. The blue lines are the electric field, the red lines are the magnetic field, everything's perpendicular. The green arrows are showing the instantaneous Poynting vector. And so that's the instantaneous power flow. Where the green arrow is the greatest, power is flowing. Where it's zero, there is no power flowing. And what we can see is those oscillations are at twice the frequency of the wave itself. They're always pointing forward. Power never quite goes backwards, but power does stop once in a while. It stops when the electric field go to zero. And that's because when the electric and magnetic fields are zero, there's no energy there. So there's no power there. So that's how we visualize it. And it's kind of a strange thing. Now, often we really only care about the overall constant power flow. We're not too concerned with these fast oscillations, and we'd like to ignore that. And that's really what we're getting into next. So to ignore that, we're interested in the average Poynting vector. And so since we start with the instantaneous Poynting vector, what we'd like to do is calculate a time average of this. So we'll calculate our time average by integrating over one period. This tau is one period. So we add up our Poynting vector over one period and then divide by the period. And that'll give us our average Poynting vector, describing the average sort of overall power flow. So we plug in our expression for the Poynting vector that had our two terms. Those separate into two different terms. Well, when we integrate a cosine, that's just as often positive as it is negative, and so that will cancel out. That becomes zero. We're just left with the term on the left that we have not yet integrated. After integration, all of this stuff is really a constant, comes to the outside, and we just end up with this one final expression for our average Poynting vector. And typically, in fact, I can never recall a time where I was ever interested in the instantaneous Poynting vector. It's maybe just on the path to this average Poynting vector. So now we jump to the frequency domain. And now our Poynting vector is complex. Remember our discussion, all these complex numbers. So when our electric and magnetic fields are complex and we're representing them with phasors, we calculate power as E cross H, where we take the complex conjugate of H. This is very analogous to when you took circuit theory and we were calculating complex power, and it was current times voltage, and we took the complex conjugate of one of them. So the same thing is happening here. So to start, we use expressions for the phasor expressions for waves. So we have an electric field and a magnetic field, and I chose to put this in terms of the complex propagation constant here. But you'll notice we have the magnitude of the impedance and the angle of the impedance. So we have our phasor expressions for our waves. That's the electric and magnetic field components of a wave. We can plug them into our equation for the Poynting vector. And then we can calculate the cross product after taking the complex conjugate of the magnetic field. So first thing, complex conjugate, and then we do the cross product math, and this is where we end up. And we have a cross product now, x and y, because x was the direction of the electric field, y was the direction of the magnetic field, and of course this cross product points in the z direction. That's the direction power is flowing. And we have our final equation for the complex Poynting vector. Then we have our RMS Pointing vector. That previous Poynting vector was kind of like the instantaneous Pointing vector. And what we'd like to do is just sort of the average. We have this oscillating power. We'd like to average this out. We did the same thing in circuit theory too. We just looked at RMS power. So the RMS is 1/2 the real part of the complex Poynting vector. So we have this equation to calculate it. So 1/2 the real part of the Poynting vector. We plug in our expression that we derived on the previous slide, and out this comes, and we have our final expression for the average complex Poynting vector. Back to total power. So the Poynting vector is a power density, and anytime we have a density term, there's an integral hiding behind it to add it all up. And in this case, we're integrating, if you will, the power flux through this surface, and that'll tell us how much power is coming through. Typically, we'll do this with the average Poynting vector so that we get the average power. We're very rarely, and I've never personally needed the instantaneous overall power. I've just needed the average power. The last thing I want to discuss here is power flow versus the flow of phase. And this is something kind of different, but yet interesting. So this circle I'm showing here is really the cross-section of an index ellipsoid. So it is a map of refractive index as a function of direction in whatever this material is. And since it's isotropic, every direction the wave would propagate, it will see the same refractive index, so we get a circle or a sphere. Now, if we pick a point on the surface, the vector connecting the origin to that point is our wave vector. This describes the movement of phase. So you can imagine the wave fronts being perpendicular to this arrow trucking along this way. So if you throw a rock in water and you watch these ripples, if you were to trace your finger with one of the ripples or follow the ripple with your finger, you're following the phase of that wave. Now, it turns out power flow is defined differently. Power flows actually in a direction that is perpendicular to the tangent of that point on the surface. Now, since we have a circle, the direction of power flow is parallel to the direction of K, only because this is a circle. And because we always seem to analyze things as circles because it's simpler, we get programmed into thinking that phase and power are always in the same direction, and that is not necessarily true. Let's look at the anisotropic materials that don't have circles but actually have index ellipsoids. Again, we'll pick a point on the surface, and the direction of the vector connecting the origin to that point, that is the direction of the wave vector. That's the direction that phase will flow. Well, following our definition of power, we have a tangent along this sort of direction. That means the power will be going in a slightly different direction than the phase. And this seems kind of crazy. And actually, the phase planes of a wave will be tilted to the direction that this wave is actually going. The analogy I like to make is, imagine you spin in a circle real quick 20 times, and then you try to run toward a specific object. You're looking at this object, you're trying to walk toward it, that's phase. However, you're really dizzy, and your body's heading off to the side, and that's really the power. That's your actual direction. More of the phase, or the way you're facing, is just kind of the direction the wave wants to go, but in some materials, it's forced to actually go in another direction. Pretty neat and strange thing. So that's it for this lecture.